Welcome back again to the studio. Finally, we have come to our specific example program, which will be an alarm clock. We will show you the steps of the development and will explain the code's operation.
The first step is to define the functionality of the application. András, please help me list the functions of a simple alarm clock.
The most important are the display of the exact time and date, setting the exact time, displaying the time of the alarm, setting the time of the alarm, and the alarm itself.
The buttons will be used for the setup, while the display and wake up will be done on the OLED display, which is attached to the development board, where the wake up will, of course, be for demonstration purposes only, with screen flashes. With the functionality in place, the next step is to model the operation and define the software architecture. The defined operating states can be organized into a state machine, where a state represents the system's current condition. Based on certain events, the system can switch from one state to another, executing specific actions in the new state. The most illustrative graphical description of this is the state machine diagram, in which the rectangles represent states and arrows indicate transitions. The description of these can be included in the diagram or in table form. For this example, we will use the latter because at this early stage of planning, the exact events and activities are not yet known, but the states and possible transitions can be defined. You may notice that the states are not defined on the same level, which is because the wake up is a special state as you can get there from any other state. If we had defined the states at the same level, we would have obtained a much more complicated graph. To avoid this, we've grouped the states together so that the blue rectangles represent the main states and the yellow ones the sub-states.
The next step is to determine the exact events that trigger the transitions and the activities that take place during the transition, which requires figuring out the exact role of the buttons. Let's see what they do.
During normal operation, you can toggle between displaying the clock and the time of the alarm by pressing the up and down buttons. Pressing the Enter button activates the setting mode. If the time and date are displayed, the Enter button jumps to the setting of the clock and the calendar, where you can use the left and right buttons to navigate the cursor. The up and down buttons are used to increase or decrease the selected value, and the Enter button is used to stop editing. You can exit the wake up also by pressing the Enter button.
This is the point where the structure is clear, and we can complete the state graph with a detailed description of the transitions. Let's see the operations to be performed during the state transitions.
Let's now clarify three concepts. The state transition is the identifier of the transition. We will mark this with a capital T and a number. The condition is an event that triggers a transition. The activity is the commands to be executed as a result of the transition. Let's see the state transitions, their conditions, and what kind of activity they perform. The condition of T0 is the successful hardware initialization when the system will be in idle state. In T1, when the Enter button is pressed, the exact time and date from the RTC is retrieved. In the case of T2, when pressing the Enter button, we can set the exact time and date in the RTC peripheral. During T3, when we press the up or down buttons, the current alarm time and status are retrieved from the RTC. In T4, when we press the Enter button, the current alarm time and status are requested from the RTC. In T5, pressing the Enter button again, the time of the alarm and the status in the RTC peripheral is set. During T6, when we press the up or down button, we get the exact time and date from the RTC. At T7, the wake up is finally activated and the alarm begins by flashing the OLED display. In T8, when we press Enter, the deactivation of the wake up is done. In T9, when we don't press the enter or the up or down buttons, the displaying of the time and date will be continued. In T10, when we don't press the enter, the setting of the clock can be continued. During T11, if we don't press the enter, nor the up or down buttons, similarly to the T9 conditions, we continue to display the wake-up time. In T12, with the same conditions, we continue setting the alarm. In T13, if the alarm is currently active and the enter button is not pressed, the alarm will continue.
Let us see the program code, which we have prepared based on the descriptions so far. The hallmark of a good code is transparency and maintainability, because it is written once, but read many times.
Yes, it's just as you described. During the development process, a larger problem needs to be broken down into smaller, manageable parts. With the state machine graph and the precise definition of events, it's been done, but the same should be done with the code. It needs to be broken down into smaller, well-defined modules, which should be done with a so-called layered software architecture, where the microcontroller is at the bottom, above it is the HAL library, and above that there may be various device driver components, in this case the drivers for the OLED display and the buttons. The former has already been introduced in the previous chapters of the curriculum, but we will take a closer look at reading the button states. At the top of the architecture is the application layer, that is the alarm clock, which will be wired in the same way as the previous ones. András has already uploaded the example program relevant to this chapter. In the program, the RTC setup will be new and the buttons will be handled a bit differently. The RTC settings for this particular example are to use the real-time clock itself, which is enabled with the selection of Activate Clock Source, the calendar, which is enabled with Activate Calendar, and last but not least, to enable alarming on channel A. The clock signals also need to be set under the Clock Configuration tab. Buttons are also used in this example application, but in a different way than before. The GPIO mode has to be set to external interrupt mode with rising or falling edge trigger detection. The reason for this will be explained in a later subsection called button driver. As we did beforehand, internal pull-down resistors are allowed. In order to use these interrupts, they must be enabled in the NVIC settings. The program lines for the real-time clock are written to the files rtc.h and rtc.c. The highlighted line is a variable declaration for an instance of the data structure describing the RTC. In the subsection HAL functions, we saw that every function has an input parameter ageRTC. In this case, this is it. The now highlighted line is the declaration of a function whose task is to prepare and initialize the real-time clock. The file rtc.c contains both the instantiation of the ageRTC structure, declared by rtc.h, and the implementation of the mxRTC init function. The code basically sets the time and date format and enables alarms on channel A in interrupt mode. There's also a handwritten section in the code lines between the comments user code begin check RTC backup and user code end check RTC backup. What happens in startup is that one of the backup registers is checked and its contents are not lost in the event of a power failure as long as the additional capacitor supplying the V battery pin is charged. The problem we want to avoid here is not to reset the time and date at every startup. If there is a preset value in the register, this is hexa5050, we can be sure that the time and date have already been set on previous startups, so in this case, we do not need to set the RTC again. However, in the case where the value is different from the previously mentioned value, which means that the RTC memory content has been corrupted due to a power failure, during which the capacitor has been also discharged, it follows that the system has forgotten the time and must be reset, and the corresponding value must be written to the backup register. The file also contains two auxiliary functions, hel rtc msp init and hel rtc mspd init, the former of which enables the RTC peripheral and the interrupts associated with the alarm, and the latter of which handles the deinitialization. The button driver is responsible for reading the state of the buttons and their changes. In the button.h file, we are managing two questions. One question: what is the current state of the button? It can be either pressed or released. The states are named by the enum button state type def and stored in the state variable, which is a button type def structure. The other question is, has there been a change of state since the previous query? That is, has the button just been pressed or released? This event is also stored by button type def, but in another variable called updated, which can take two values, true and false. All buttons are contained in the buttons type def structure, which can be retrieved using the buttons getStates function. The buttons C file contains the implementation of the buttons getStates function published by buttons H, which simply copies the locally maintained data structure named buttons and of type buttons type def into the same type structure given in the parameter, and updates the flag named updated, which monitors the button state change. The state of the buttons is monitored by the interrupts assigned to the buttons and updates the contents of the buttons variable. Unfortunately, the buttons do prel, and our development board does not include hardware debouncing. We've already been introduced to the concept of the bouncing in Chapter 7. To repeat, it's the fact that one button press is perceived by the controller as more than one, because the metal contacts inside the button do not make contact once at the moment of pressing or releasing. The code also includes a kind of debouncing by having all beats generate an interrupt, and the HAL GPIO EXTI callback that runs at the very end will always record the correct state. The components of the application, that is the alarm clock, are contained in the files alarm_clock age and alarm_clock c. The alarm clock age file contains only a single line of code, which is nothing more than the publication of the alarm clock main function. This function is visible externally from the software module and drives the state machine, so it will need to be called periodically in order for the application to work. The alarm clock C file contains the implementation of alarm clock main function, along with other functions with file level visibility, and also includes the data structure. The possible states are defined in the alarm clock state description. The main states are named by the enumeration main state type def, and the substates by the enumeration substate type def. The two types of data, which are related, are combined by state type def, of which one instance exists and is called state. The structure time object type def describes the information displayed in the display by specifying the start coordinates and the type of data selected. The state machine in our program is an important feature. Several functions are involved in the implementation of the state machine, but two of them have a special role. These are the so-called entry points of the application software module, which means that these functions can be called from outside.
Alarm clock main function drives the state machine. This always retrieves the state of the buttons and the date, time, and the time of the alarm. Based on this information, and by examining the state variable, it selects the appropriate state handler from multiple functions. Also, if necessary, it switches state. The HLRTC alarm A event callback is a function that is called from a specific context, which is the interrupt. If the set alarm is about to start, the control will be set here regardless of where it was before, and only change the main state of the alarm here. Alarm in progress.
The function that handles the time and date display mode is called showDateTime, which takes the time and date as parameters. It prints this information to the OLED display. The function that handles the operation of the alarm display state is called showAlarmPresetTime, which takes the time and state of the alarm set as a parameter. This function prints this information to the OLED display also. This state is handled by the function setDateTime. It takes as parameters the currently set time and date and the state of the buttons. When this function is called for the first time in the set time and date state of operation, the time and date must be saved in temporary variables, date to set and time to set. You could ask why. It is because these variables are used when the buttons are pressed, and only during the state change these values have to be written into the corresponding registers of the microcontroller using the functions HAL RTC set date and HAL RTC set time. To help with the setup, an array called timeObjects is created to describe where particular information should be placed on the display. The stored objects are of the timeObject type def and contain three things: what part of time is currently selected, year, month, day, etc., starting x coordinate and starting y coordinate. By pressing the left and right buttons, we can change the selection, which causes the code to increase or decrease the value of the variable selection idx. It allows to step through the elements of the previously mentioned timeObjects array. The selection is shown on the display as a blinking cursor below the value. The up and down buttons can be used to decrease or increase the currently selected value. Toggles and value limits are controlled by the update selection helper function. Suppose it is leap year, the set month is February, the days are currently selected, and the value is 28. Pressing an up key will let update selection set the value to 29, and pressing up again will flip the value from 29 to 1. Pressing the enter button will exit the set clock and date state, performing the actions associated with D2. The alarm is set by the setAlarm function. Its implementation is very similar to the implementation of setDateTime discussed earlier, only the information to work with is different. The alarm is handled by the alarm function. It draws a big alarm on the display and flashes it twice a second. Once with a light background, the text is printed in dark, and then vice versa. Pressing the enter button will exit the alarm. The main.c file contains the main function, which is the entry point for the project and is used to initialize the modules and later to start the operating system. The alarm clock state machine is periodically called by a simple infinite loop. This implementation may only be a suitable choice for simpler systems where there are few tasks to be performed and no strict timing constraints. For more complex tasks, the use of an operating system is recommended, and examples of this will be given in later chapters of the curriculum.
In this section, we were introduced to the RTC peripheral, first in general, and then STM32F4 specific. We also learned about the most commonly used functions in the AHL library, reviewed the RTC-related hardware components on the development board, and finally reviewed the design of a simple alarm clock, and went through the details of its implementation.
We've come to the end of the RTC curriculum, and we hope that you are excited about the many opportunities that this periphery offers us. At home, you can try out what you've learned Use the RTC in your more complex electronics, as the theoretical knowledge will be consolidated during practice.
Experienced crystal clear electronics users already know how we are learning to use new peripherals step by step, which will eventually enable us to design complex devices, even for industrial use applications. We encourage you to experiment and practice. You may already know that all additional content is available on the curriculum's website. If you like the video, subscribe to our channel and follow our Facebook page. We will now say goodbye. In the next chapters, you can learn about electric motor control, controlling solutions, and embedded operating systems, among more interesting topics. See you there!
Bye!